So let's use this microphone instead. So before we start with today's lessons, are there any questions concerning last time when we discussed state machines or their applicability to the coursework? If not, then today we're going to start discussing reachability problem, or pathfinding. But actually here, this lecture wants to be like an introduction to also the last topic that we're going to cover before like the coursework deadline. And so I'm generalizing over pathfinding and the other kind of problem as a generic reachability problem. And the other thing that we're going to do, differently from what you might find in some other literature, which is mainly game-based, is actually do like a more serious analysis of what is A star and Dijkstra doing. Most of the time you're saying, oh, A star is great, but actually you're not discussing which are the limitations of both. And that is actually not good for having like an unbiased opinion of which are the pros and cons for each approach. And definitely what is actually what we're going to do today. And still, nevertheless, I'm trying to do this kind of stuff as interactive as possible. So you're having like the pseudocode on the slide, but we're going to discuss how the algorithm works directly from the C# implementation that I provided in the code base, okay? So we're going to discuss that directly. So that is actually what we're going to do. So let me give you a formal definition of the reachability problem and then an instantiation that we're doing for pathfinding. So the general definition of a reachability problem is the following one that you're finding on top and is also like the same one that you're finding in Wikipedia, really. So which is, given that you have a computational system, whatever that is, so in our circumstance is a set of states or of transition between states. So you already have an intuition of state from the state machine. So you might see something similar. That might be also potentially infinite. That is actually due in the realistic setup, then you have like a plethora of possible things that might happen, not necessarily a finite graph. And then you're having a set of allowed rules to navigate and to go from state to state. So those are the transformations. Decide whether a certain state that you're reaching is reachable from a given state for the system. So what does that mean then in terms of reachability problem and in pathfinding? So let's go back to basics, okay, shall we? So what are the set of states? The set of states are really the position within the scene of your game where the non-player character is. And how are you defining those? Well, usually you are providing like a discretization of space. So you are providing tiles, be those in 2D or in 3D, from which you're setting up which are the states. And in here the state is the agent reached a specific tile. So that is actually the state that you're considering at this stage. Okay? Then the set of allowed rules here is that actually how to reach a specific set of tiles. Or specific tiles, sorry. So you can reach a specific tile not necessarily by jumping, but you might do that, but it might be something like specific, and you could hard code that nevertheless. But usually, that is the common entendre, is actually that you are going from tile to tile by traversing the adjacent edges that are actually near to each other. So that is actually what you're doing. So these are the allowed set of rules to navigate the graph. So allegedly that will boil down to traversing the edges for a graph problem. And then you see that formulation on top is somehow general, is not telling you how you should find the path between the source and the destination. But for pathfinding, we are often interested into a minimization problem, thus into an optimization. So we are interested in getting across all the possible paths from source to destination, so from SRC to T, the one minimizing the overall cost. And then I'm telling you what this kind of mathematical clutter means, okay? So this, what you're saying from SRC to T, is actually our path within the set of all the possible paths, pi in uppercase. So we are considering a specific path pi. And given that usually costs are additive in this kind of problem, then, and given that usually the allowed set of rules are a transition from a state to state via an edge, then I'm considering a cost function or a distance function, usually framed as delta, which is actually the cost of transiting from a given state to another state. So wrongly, most of the time, that you're seeing in literature or in games blogs, that the cost is associated to the nodes. No, the cost is actually associated to the edge. And the thing that you're doing with the algorithm is keeping track of which is the total cost of reaching a node, but the cost is not associated to the node. The cost is associated to the edge, okay? And if you're seeing A star as an algorithm, this kind of cost is often referred to G, which is the cumulative cost of reaching a specific target or any node in the graph or any state from a specific location. So often the subscript is omitted, but you're always referring to the cost of reaching a node T from a given source. So this is the problem instantiation that we're going to see today. Nevertheless, the last lecture, so lecture number 10, will also consider a more generic case, more related to problem solving. So navigational rules are not just expansion rules to have or achieve or reach specific configurations of interest. And we're not necessarily using a graph, but we're using like logical set of rules. And we are generating a graph as an outcome, but we are not using a graph nevertheless explicitly. So I'm going to provide, so that's why I provided like a general formulation, specifically for this kind of problem. Any questions so far? Good. So now the thing that you're doing is basically trying to navigate the search space. So it provided like a very old blog which disappeared, so it's only on our way back archive now. But anyway, basically what you're doing with a searchability algorithm is going out of the blue. So you see, even if you are within a jungle and you're trying to navigate that, is like having like a very full amount of grass, and then you're trying to go next. And the only information that is actually you're possessing is basically what you want to head towards, and just local information where I might go. This is actually how these algorithms often work. But the problem is, then your question that might arise is, why are we not using like state machines then? So if we're having a graph for graph, then even a state machine shall, a line of principles still be used for this kind of stuff. Well, I'm giving you my 2 cents why we're not using state machines. You're not using state machines, so it is actually not necessarily related to the cost or to the weight, which is actually not present there. But it's actually more related to what the graphs absolve as their aim, so to follow a protocol of behavior. Well, in here, we're doing something different, which is having the graph not for the behavior of the agent, rather than for telling the agent the behavior. So they are absolving 2 different purposes. If this is how to instruct the agent to do the behavior and to move, the other one is a protocol for the behavior. And the other problem is, so you could use, for example, this kind of graphs even dynamically. So if you might have like an obstacle obstructing the path, you could update the graph dynamically. But the problem is that if you're using like a state machine, then often you are not assuming that the structure is updated dynamically. So it's always statically implied. And therefore, the thing that you're ending up with is actually considering all the possible implications of have at any possible configuration need to forecast that I might have an obstacle to overcome, and then you need to recompute the path or something. So it's actually unfeasible to do that in practice with a state machine. So, and definitely we need to potentially hard code then as a consequence all the possible paths that I want to traverse, which is unfeasible. And thus, then the thing is, rather than doing all the possible actions that I could do, it's actually better to encode the information of the environment in a minimal way, and then the agent, given the environment information, will decide how to enact. So it's actually more acting like a map for the agent, rather than acting as a protocol for the agent differently from beforehand. Then I'm going to provide you another contextualization of the thing that I was discussing before, right? Which is, usually, you might have different ways to set up the tiles. So the usual thing, like in old SimCity 3000 and other versions, but in here it's actually quite blocky, so it's actually better to visualize. So you see, usually you might not go from one point to the other. So for example, let's suppose that you're having a tunnel, and under that circumstance, then you could jump, and then you might hard-code the graph. And definitely in this scenario, everything like is a 4x4 tile, as you might see. And in here, you might also have a block. So if I am in here, for example, like a pedestrian, it cannot go into there because it's actually blocked. Anyway, the thing that I'm setting up is basically how could I traverse. So given the grid, I might define the path, and a sub-path might be something similar to the road if I'm having cars. So I'm designing definitely where the cars might go, for example. Or if you are considering like a subset of all the spaces, then you're defining all your road system, and then the graph will be just the tiles after the composition, which are roads, and everything else is actually blocked like an obstacle. But, and so you see each tile will be a node of your graph, and all the adjacent nodes will be actually other nodes that are reachable. So you might freely assume that I'm having like a node starting from one of these tiles, and having an adjacent or a neighboring one, and then I'm having an edge connecting the two. But that is actually, and then each node will have like 6 connections, but that is actually not necessarily the case. In here you have another use case scenario on where you might have, like, for example, an hexagon rather than having a 4-way tile. And then in here I'm having a different kind of games, and then you might see if having a ship or any kind of object that is navigating the waters, then I'm considering as navigable tiles the ones in the sea. Otherwise, if I'm just like a worker or anything else, or like infantry or this kind of stuff, then I might consider only going along the land tiles. So still you are discretizing the set of elements, and then you are deciding how to navigate from point X to Y. And then the thing is that similarly to the web comic that I provided beforehand, the best thing that you can do if you don't have, so otherwise you need to explore the set of all the possible states, which is actually unfeasible. So usually the best thing that you can do is using a greedy approach. Thus you're starting from a tile, and then you are considering only the neighboring tiles. And from there, so for example, let's suppose you're having like an item or an asset that you want to displace, then you are often designing which should be like the final state where the agent should go. And then you're clicking on that. What is happening under the hood is designing how the agent should be displayed in that position, is computing the path, and usually an algorithm will just consider the neighboring tiles and add up onto that. Otherwise, it's actually impossible to consider all the possible paths, because that will just prune this state purge as possible. But please note that the other thing that they want to have, like a backtracking system. What does that mean? So if you did, I don't know to which extent you did like NP-complete problems in algorithms and data structures, or like in an original module of logics, but usually if you are enumerating over all the possible actions and you are building up a solution, you might need to backtrack to your previous step for then continuing doing the computation. So I do not want to do a brute force approach. I want to also do that gracefully as possible by doing a minimal update. So even the algorithms that are going to show you are going to ensure that I do not need to revise the path all the time, but I'm just updating my nearest ancestor all the time. Thus achieving minimality of updating the best solution for the minimum path towards the destination. And the other important thing is, if you are not providing any additional assumption, like any kind of heuristic for A star, or any kind of edge weight, differentiating why should I prefer one tile to the other as my subsequent step for navigating from one tile to the other, then it's actually not better than doing like a DFS or a BFS algorithm for reaching a destination. So so let's suppose that you are in SimCity and you have like a flat land without any kind of sea, and you want to find a path from a point A to B anywhere in the map. And let's suppose that you have no trees whatsoever. Then, if you have no weights, then the only thing that you can do, if you're not using any kind of heuristic or any kind of weight, is just getting full exploration of the graph as much as possible. And then as soon as you're finding the node, then that is actually going to be your solution. So at the end of the road, that is actually what you're doing. And there is actually no other better solution than that. Also, please also consider that is not the end. So usually what even if you're doing in Unity is setting up like the walkable path if you're using a navigation mesh. But then there is actually something which is beyond your control, and Unity is actually doing automatically, which is deciding which position of the tile your non-player character is going to be, because actually after you're computing the path, that is just a discretization of your 2D/3D world, but you're not necessarily telling where the agent should be within that node, and which is actually the trajectory within that node or within that tile to go from cell to cell. So then additionally, you need to also say which is going to be the path within there, and you need to be like Unity is already doing that for you, so it's actually not a problem. You could also fix this problem by minimizing the size of the tile as much as possible, so to be very precise where it could be, but then you have like the countermeasure, which is you're exploding the size of the number of nodes that you need to explore. So usually either using a hierarchical approach, which we're not considering now, or you're just making as big as possible this kind of tiles. But if you're using like a simplistic algorithm, you might end up with a path which is actually non-optimal. So then is dependent on the other algorithm exploiting a star or exploiting Dijkstra for determining how the agent should move within the tile. So then you might freely assume that either I'm just applying a force to the agent, or I'm rerunning another kind of A star or Dijkstra for within the tile, and that recursively to a lesser extent. Okay. Before we are discussing the algorithms, are there any questions so far regarding pathfinding, its employment in Unity, or what are those about? If not, then I'm going to follow like a more practical approach. So I'm going to first discuss you how this works with an animation, Dijkstra, and then I'm going to show you the actual C# code. In here you're having the pseudocode in an abstracted way, but the thing that I'm going to say is basically the pseudocode. I'm just narrating the C# code in order to make you better understand the code that was made available to you, okay? So, then, given the thing that we said before, how is Dijkstra working, is actually considering all the weights for the neighboring edges, and if there is actually no weight better than the other, then any of these nodes would do. So, under this assumption that in this scenario, the nodes from, as actually I think that the red node is missing, which is actually the starting, but that will pop up eventually. So, all the paths from source to target will be equally fine. So then the thing which we're expecting is like a bubble coming up and trying to wrap up all the paths. And that is actually precisely what is happening, you see. So the algorithm will start from a given initial node, and then it's trying to compute, which is actually the cost that you are computing locally. Given that all the nodes are somehow equivalent and there is no intrinsic notion of which direction should be preferred, you're just getting all the nodes like it was like a BFS algorithm. So it's actually working like BFS to some extent. And then eventually you'd have that you are colliding with the target, and then that is actually when the algorithm stops. And then, given that you reached the final destination, then you could break the algorithm and reconstruct the path. You see, so how this algorithm is reconstructing the path. So you see here, you're having a set of nodes, and each node has the better ancestor. And basically, the thing that you're saying is each time you are transitioning towards another state, you're saying which is actually the best parent or direct ancestor, which is going to be the one via which, by crawling back and by tracking, you are going back to the source. And that is actually working all the time because you're always starting from the source, and so you are really assuming that your parent is reachable from the source because eventually when you met your direct ancestor, that was reachable from the source. But enough with the chit chat, let's go with the code, shall we? Can you clearly see that from the back, the code? Okay. So let's discuss that beforehand. And let's give like a intuitive way. So Dijkstra, you have like initial initialization phase, which isn't like that because that is shared across algorithms. So both A star and Dijkstra have the same initialization. What is that about? Let's go to the code, and then you'd see the initialization is just, I'm having like distances, which will be G for A star, or still the ancestry map for Dijkstra. And that is actually working as follows. So for the distances, either I know which is actually the distance of a current node val from the source, or I have like plus infinity, so the maximum double value. So that's why I'm clearing. Initially, I have no information. Everything is actually equiprobably to be a plus infinity size, with a caveat that the only thing that I know eventually is which is actually the source node from which I'm starting the computation. That is as distance 0 from itself. So what distances will have is the G in A star, and still the distance in Dijkstra, which is the minimum distance from the source towards the current node, which is 0, because you're starting from that node. And then similarly, I'm having like a parent map, which is associating for each node its direct ancestor being the one minimizing the distance from the source. So that's why it's a greedy approach. I'm just getting like in a first come, first served approach. And then I'm retaining which is actually the parent minimizing the distance with the source. And if I have that, then I'm returning the value. Otherwise, I'm returning -1. So you'd see that in this code, I'm really assuming that all the nodes will start from ID 0, allegedly. So I shall never have like minus like IDs that are less than 0. That is actually the assumption that I'm doing in the code. Then we will discuss crow later on, but that is actually just the initialization step, okay? Any kind of questions regarding the initialization step of the algorithm? Then, starting from that, I have what I will call in A star my open set. But in here, I'm just keeping the non-visited nodes for the moment. And the thing that I'm doing, but we'll see that later. So that is in the initial Dijkstra algorithm. If you're taking textbooks that are already discarding this thing with a better version of the original algorithm, but they are completing the queue with all the nodes within the graph. So even in here, you see we are assuming that the graph is finite. Otherwise, if it is infinite, then this will take infinite amount of time, and you will never have any solution. Okay. Then the thing that it's doing basically is trying to get, while I have nodes that I haven't visited, which are in queue, while that is true, then I'm getting all the nodes that are sorted according to the get distance. So after initialization, you know that the only node being not plus infinity will be the source that you're starting from. Then you're ordering by the distance, all the items, and then you're updating and making that as a list. So I'm using link queue kind of syntax in order to have compact notation using like functional programming style, okay? Then after the sorting, I would know that the first node will be actually the source in the first iteration of the algorithm. Eventually, the node that I'm reaching will be the target that I'm looking for, and as soon as I found that, then I will break. Then I know that that is already visited. I do not want to visit that node another time, so I'm removing that from the queue. And then I'm iterating across all the neighbors of the current node that I'm having. So in this case, U. And then I'm checking whether I haven't visited this node yet. And only on that circumstance, then I'm considering that as a potential neighbor. On that occasion, the edge value will be the weight, and the key in this circumstance will be like the neighboring node via the edge. So the tentative or the temporary value that I'm considering for the minimum distance in order to reach the target from the source is going to be your old. And if that alternative value is less than the get distance from the key, which is initially the first time that you're seeing the node always true. Why? Because this value before setting the distance will be always plus infinity, or maximum value. So the first setup is always true. Under that circumstance, I will always have a value which is minimizing the value. And then I'm setting the as a parent of the node, the new node, neighboring node that I'm visiting, which is the key that I'm retrieving from all the neighbors, the current node that I'm having now. So basically what it's actually considering, I'm starting from the node, considering all the neighbors. For each neighbor, if that variable, if the distance from the current node and the neighboring node is actually such that I'm having like a minimization of the distance, then I'm updating that. Then you might ask, why on earth are you considering all the possible candidates? It's not actually that once you're getting one best node, then it's actually going to be the end of it. Then the answer is actually no in a generical case. Why? Because you might also have like a graph on which you might have multiple ingoing edges. Thus you might have multiple ancestors, not only one, as you might have in a tree. And that might be also a shorter path if compared to the path that you were previously traversing. Maybe beforehand, by using a greedy approach, you had like a local minimum, which is actually not a global minimum. Eventually, you might have a single edge connecting me and actually having a less cost overall than the thing that I previously computed. So keeping all the possibilities, basically. That is actually what I'm doing in here in this algorithm. And then, once I exhaust all the possible things, and if I reach the target, then I would know, potentially, that I found a path. So you see, if I'm continuously navigating the graph and the target is not reachable from the source, then my ancestor from the target towards the source will be always -1. And so after getting all the possible nodes reachable from the source node, I would have like an empty path. Because my ancestor of the target will be -1 all the time. Otherwise, if the ancestor of target is not going to be -1, it means that I have found a path from the source, okay? And that is actually what crawl method is doing. So basically, I am trying to get all the parents from the original target value. And while that is actually not -1, and while that is actually not true, then I'm inserting also the node that I'm receiving always at the end, at the head of the list. And then I'm retrieving its parent. So all the time I'm always crawling back. So you'd see that if target is actually -1, then I'm returning an empty path because there is no viable way to reach the source. And otherwise I find a path, and then by just adding and just retrieving like the cost from the distance, I am determining which is actually the total cost. And that goes without saying. If I'm never reaching the targets from the source, then the map will never update the distance map, and thus the value will be always +infinity, as set in here. Otherwise, the try and get value from C# is going to update you with the value which is retained from the map. And then I'm going to do like more theoretical and high-level discussions of the algorithm. But before I'm doing that, do you have any questions concerning how this algorithm behaves? And why is that actually correct? Otherwise, if you have none, we're going to discuss that informally. Because actually a proper proof of the correctness of the algorithm requires like induction and even more serious kind of induction compared to the thing that you're doing by first year. So it's actually quite high level and difficult. So just providing like a high level algorithm. Any questions on Dijkstra? No hands up. Okay. So basically, I'm not repeating myself, but if you are double checking the pseudocode is actually the thing that we discussed now. So out of simplicity, I just kept that out. Okay, so let's discuss the algorithm. So Y is actually computing all the possible nodes. So the original algorithm was just to compute all the distances from any point of the graph reachable from the source. And the original algorithm was not necessarily designed for computing the path from source to target. So that's why it's actually somehow exhaustive in a sense. So that's why we're not using an heuristic towards the target. Okay? And so the other caveat, which is often not discussed enough, is that this algorithm might be changing its computational complexity by just changing the type of data structure that you're using for a queue. So if you're just using a list and you are resorting all the time, as I'm doing, then you're not doing better than a quadratic overall cost of visiting all the possible vertices because you are resorting that. But we're not to discuss that in too much details because it requires more discussions on the algorithm and data structure models. But you could also use Fibonacci heaps. And then with that, you could also lower the lower bound to having something approximately linear to the optimal cost being related to sorting all the nodes according to the distance. Because that will minimize all the restructuring that you're doing. Well, the quadratic cost in here is because each time that you're visiting a node, you're removing from queue and then you are sorting across all the nodes. So it's actually an upper bound of the quadratic cost in the worst case scenario. And those points were already discussed by showing the crawl function on top. And then, as I was saying, in this algorithm is just to show you that it's assuming to have like a finite graph under the assumptions. Nevertheless, there are also renditions or better versions which are for a further improvement of the algorithm, often referred as to uniform cost search, which is a straightforward extension of a former algorithm, not necessarily requiring to enumerate all the nodes in the graph. So I'm not filling in the queue according to all the V nodes that are within the graph. But I'm just starting from the source and navigating the neighboring object and remembering whether the node was already visited or not. So we'll also do that in another way. But as you've seen previously, if you're taking this algorithm, there is actually no preferred direction that you should take. But even if you're using an heuristic, that doesn't necessarily entail that you're finding straightforward the path. So you still have some search to do, even though you are pruning a lot, so removing a lot of space that you need to discuss beforehand. But nevertheless, that is actually a bit of algorithmical correctness, as I was introducing earlier on. So why the algorithm is correct. Just from an intuitive perspective. Initially, you know that so you are having a map or G as you will have like in A star, which is actually the distance from the source. And initially, the only thing that you know is that all the nodes prior to visiting any kind of neighboring edge will have like a plus infinity distance from the source, while the initial node that you're visiting will be at 0 distance from itself. then as soon as you're finding one neighboring node, you'd know that that neighboring node will have, as the distance, the weight that your delta that you are associated to the edge. So in the first step, the algorithm is updating G by just summing 0 plus this cost, which is just the cost of traversing the initial edge. And then eventually, under assumption, this is actually not a correct inductive argument, because that will require also contradiction. But it's going to be too much complicated, so I'm just keeping that informal. In an informal way, eventually I will reach a point, and that point will have, by definition, an ancestor, because if you're reaching another node, you'll definitely have an ancestor. And given that you're reaching that via the latest ancestor, the constructive argument will guarantee, given the way you're updating the parent node, which is always going to be the one minimizing the distance from the source, that will be also the node minimizing the distance of minimizing the cost of the overall path. And by transitivity, then you'd have that when that node is actually the target, then by construction or having like the minimum path from source to target. And thus is actually guaranteeing the path optimality. Just intuitively to give you why the algorithm works. Any question on this? If not, then we're starting to discuss Dijkstra limitations, and the third point, we're starting to address that limitation, okay? One limitation, which is often ignored in video games, and is that all the edges should have like a 0 or positive cost. So why is that ignored? So often when you are taught the algorithm, you are freely assuming that all the weights are 0 or plus infinity, but never negative. So you're never finding any kind of issues. But the algorithm has issues whenever the edges are -1 or -20. They do not work. You have other algorithms for those, okay? Due to the intrinsic nature of how the algorithm behaves, and given that you're finding like a minimum weight. And the other assumption is that the graph is finite. So what if we are having like in a robotics field where the graph might be potentially infinite in size? So we do not want to iterate over all the possible nodes initially and initialize that in cube, but just starting from whatever we are having and then building up from there. Okay? So that is actually what you're doing. Usually in robotics, you're not creating the graph of the scene like you're doing like in Unity. But you're starting from a point and then you're getting just the neighboring edges, even because the environment might be dynamic. So another way that you're doing in A star is actually assuming a sense of direction. You're doing that through an heuristic, telling you we should be the direction towards the target, okay? So that is actually going to be your compass, and whatever is going to be the compass pointing towards the target is going to be like the minimization of the cost overall. So the heuristic is actually acting as a compass for determining which is the best neighboring node. So what is actually the heuristic about is actually approximating the remaining distance from the current node where you're at, u, towards the target. And that is actually what the heuristic is going to compute. Then, sorry for the typo in here, in equation 1, that should be a v, so f src comma t within rounded parentheses v, okay? That is the only things required, so then the last part of the slide, current slide 9, is okay. So the thing that you're doing then is after you're traversing the edge from the current node u to v, you're trying to estimate the final distance from v towards the destination. However, that is going to be computed. Given that, I'm going to have an estimation of which is the best neighboring node. And then we'll see together which is a way to select h. But we need I think an additional discussion before doing that, yes. And then that will give you the total cost, estimated cost f. So what is actually the shape of the argument? Eventually, once you reach the target, the heuristic will return 0. That is actually one of the other requirements, because the distance between the target and the target itself will be 0. And cumulatively, you would update g to be the actual cost of reaching the target. So that is how A star will work. So it's just using H as a compass, but then updating G as you're doing in Dijkstra. So basically, Dijkstra is A star where H is always equal to 0. So that is actually the equivalence of having no heuristic at all. And then in here, I'm discussing why often you're using as an heuristic like the Euclidean distance between the geographical position of 2 points. Because you have requirements that you need to abide by to ensure that the heuristic is correct. Otherwise, the A star will go bonkers. I'm just providing high-level discussions because we don't have enough time to go that in full details, okay? So we have like admissibility and monotonicity of a heuristic. Usually we're saying that an heuristic is admissible if it never overestimates the cost of reaching the goal, but it always provides a lower bound. That is important because if I'm overestimating, then I'm over-exaggerating all the time the cost of reaching that. So it's actually counterintuitive. Usually you might say, in order to be safe and sound, then let's overestimate the cost and then no. But it's actually not going to work because the compass is not going to work properly. And then in the worst case scenario, you might select a node which is actually not the best one. So you're ending up with a path which is not the optimal solution. So you have a path, but it's not the optimal path. While A star guarantees optimality if you're using like a correct heuristic. Then you have monotonicity, which is also related to triangular inequality, but let's reframe that in terms of a graph. So if the difference between the heuristic values for each pair of connected nodes does not exceed the effective false, blah, blah, blah. What does that mean? Okay, so at the current stage, I'm estimating the cost of reaching the destination from a given node U. I know that U has a neighboring node V, for which the distance is known via the edge, so I have delta. Okay. Then the thing that is actually saying, why is that the former one also a lower bound? And so you have somehow those are two are related, because the cost that you're getting from getting the edge plus the destination from the neighboring nodes towards the target is actually an upper bound towards the value that you computed beforehand. And you see informally, I'm not asking you in the exam why, so this is actually just given informally, any monotone heuristic is also admissible somehow. Why? Because I provided like an intuitive argument in here to give you a better insight what is actually admissible or monotone. So let's suppose we have a triangle A, B, and C, okay? Thus entailing that you're having edges A, B, B, C, and C, A. So, what admissible means with an example of a triangle, it means that no road between 2 points can be shorter than the straight line distance. So in this case, actually the heuristic being, for example, the Euclidean function matches with the actual distance. And then the monotonicity is actually related to the cost of reaching A from C, for example. Reaching C from A. So let's suppose that we don't have the edge AC, but you only have like AB and BC, and that AC, the distance is actually our heuristic. Then we have that definitely the distance between A and C will be always less than the cost of reaching B via A for then considering the distance from B to C. So in here, when I'm using the delta, I'm referring to the actual size of the node, the length of the edge of a triangle. When I'm using like the upper bound is just to remark that I'm not necessarily considering like the edge distance, but that edge distance is acting as the heuristic. So it's just providing like an estimation between these 2 points. So if you're seeing A, B, and B, C are delta UV and HT of V, basically we're acting as that, while the estimation of reaching C via A is actually your heuristic, H of T. So that is actually the mapping between these two. But do not worry if you're not grasping that, because I'm giving you also at this occasion like a live example, and then we are considering the algorithm, okay? So in here, then what we might expect is that rather than considering equitably, in an equitable way, all the neighboring nodes, I'm just considering the neighboring nodes minimizing the distance towards the target by using that as a compass. So then you might expect to have that in a straight line as much as possible. But that is still an heuristic, so it doesn't help you going beyond the obstacle that you're having in between. Still, you need to apply the search.
So it's not actually omniscient, because you're still using like a greedy approach, navigating only on the neighboring nodes. So you'd see that the A star will look as follows. I'm starting to go from here to there at the very end, and I'm having this kind of path, but then I'm stuck on the obstacle. So then I'm starting to broaden a bit and go for the neighboring nodes up until I find the path. So still, given that I'm having the heuristic that in this case is admissible and monotone, which is just the Euclidean distance between two nodes being states in a physical environment, then you'd have as a consequence a refinement of the search space because you're visiting less edges. Still, you are not avoiding the possibility of colliding still in the search time against the obstacle, and then needing to overcome that. But the thing that you're doing, nevertheless, is avoiding navigating all the nodes that you're having on top. Why? Because eventually, when starting navigating from there, I would see that in here, I need to go a bit up in order to reach the destination, while if I'm moving a bit on the right from here, I'm actually going nearer to the destination. So in there, intuitively, the heuristic at the bottom left is actually telling us that you need to elongate the path in order to reach the destination. In here, the heuristic is actually telling you, okay, if you're moving even a bit on the right, then you're reaching the destination. But it's actually what, and then that's why you're expanding only on the right and not on the left. So the heuristic is actually indicating as a compass which are going to be the states that you need to navigate in order to discard the other states on top. Questions on this? And then we're actually going to see the pseudocode in order to clarify what the algorithm is doing. Not the pseudocode that you're having right, rather than the actual code in C#, okay? Questions on that before discussing the C# code? I think that then by using like the actual code rather than like a high-level discussion should help in understanding the algorithm better. But you're still having also the high-level discussion in the slides if you prefer. Okay, so as I was discussing before, the initialization is the same, is always in it. It's the same as Dijkstra. And then the open set is actually your queue beforehand. And that will only contain the nodes that you're considering at the moment, rather than being all the sets of all the nodes that you're having in the graph. And the closed set is actually initially empty, because that is going to be the set of nodes that you had already visited. And then in addition to the other score, I'm also computing F score. And initially, if the heuristic is actually sound, then then I'm using age of SRC. Why? Because the distance between the source and itself is 0. And the only thing that I have is basically the heuristic, which is actually my distance towards the destination. Nevertheless, all the other nodes will be at distance plus infinity. So whenever I'm doing the same stuff as beforehand, so getting from the open set or Q, the elements are ordered by F score, I'm always going to retrieve the initial node, because all the others will be at plus infinity, because I haven't visited those yet. Similarly as before, as soon as I reach the target, I'm breaking up the iteration. And then I'm removing that from the open set, the current ID, and I'm adding that to the closed set containing all the nodes that I have visited. Okay? Then I'm iterating over all the neighboring nodes. And then I'm doing similarly to Dijkstra. You see, I'm checking whether the node, actually I'm doing something different. I'm checking whether that is not within the closed set, which is actually the dual of the thing that I was doing before, checking whether that was in Q. But still the thing that I'm doing here, if it does actually contain, so if it contains, it means that was already visited, so it's the dual approach, but the code is equivalent, because I'm having two different data structure for that now. And then I'm computing, as before, the distance, which is the actual distance computed by summing up the edge cost towards the current node, plus the edge cost of traversing the edge. So it's actually, the get distance is your G from Dijkstra, and that is the delta value from the current node towards the next candidate neighboring edge. Then you're having the same get distance less the previously computed one, less than the alternative that I'm computing now. And then I'm adding an extra condition there on the right, just because the heuristic, generically speaking, might go bonkers if it's actually suboptimal. So I need still to consider all the possible nodes. So that's why I'm keeping this other condition that I might want to reconsider the node yet again. But if the heuristic is optimal, I could also discard the second condition. Still, the thing that I'm doing is considering now old and current as in Dijkstra, so that doesn't change. The only thing that changes is actually now old will be the G cost plus the delta, and then I need to compute the heuristic from the current best and preferred neighboring nodes, and you see the neighboring nodes is selected as in Dijkstra. So I'm not using the heuristic in here because I might falsify my assumption. So I'm only using the heuristic when sorting all the nodes on top here for selecting the best neighboring nodes or the best node to subsequently visit, but not to check the correctness of the algorithm, what should be the cost to be updated. Otherwise, I'm updating the actual cost with an assumption, which is just an heuristic, which is wrong. So the update of the actual distance, the G, will be as in Dijkstra, because I do not want to do an underestimation, but I actually want to get the actual cost. The only thing would be then, when I want to consider now my new current node, I'm actually updating the F score with the heuristic value. So I'm selecting and using G, and adding the G value with the H, and that will be my F score. And then if this node was not already visited, for example, then I'm adding that in the open set. And then eventually I'm doing as the same. So eventually the iteration will stop. Either I visit all the nodes that are not reachable from the destination, and then I'm still doing the crawl back. So the setup is the same as Dijkstra. So as soon as you find the target, or if the target is actually not reachable, if I'm trying to do crawl from source target, then I'm reconstructing the path. So even that part is equivalent. So as you see here, the only contribution is the heuristic and the thing that I'm sorting the previous Q data structure, which is called here open set, with F in order so to act as a compass. But still, G is always updated with the edge cost and is not considering the other part. Then I have like the final slide, and then we're it. I'm trying to do as brief as possible, so if you have questions on this. Then the main culprit is actually considered from the heuristic function. So the problem might be the heuristic is actually suboptimal. We might end up, given the continuously search, to visit a node multiple times, even an exponential amount of times. So if the heuristic is actually suboptimal, then Dijkstra is always better than A star. So that's why it's important to guarantee the optimality of the heuristic. But if you're taking the usual Manhattan distance or the Euclidean distance, there should be no big problems. Then A star is actually guaranteed to terminate only if you're having like a finite graph, but not for infinite graphs. And also you are always assuming that you can reach the target destination. And if it is not, then you will never terminate, because you will always continue to look for reaching the target, and that is the only potential condition of breaking the point. So if you're having like an infinite states and potentially everything is connected together except from one single node, which is actually the target, you continue to crawl and never reach the target, and the algorithm will never stop. So we need to devise other algorithms to actually check whether, if you have like a potential infinite set of space, whether you need to stop or not. And still, even A star is affected by the negative weight. So even in this scenario, A star doesn't solve the problem because it's just an extension of Dijkstra with an heuristic function, and you're still forced to use Bellman-Ford or Johnson if you have negative weights on the graph. Okay. That is actually the end of the discussion today. But do you have questions concerning A star, Dijkstra, or their applicability on the coursework? Yes? So, thanks for the question. If you're looking at the coursework, then specifications, then you also have like usage of nav mesh, and you're having also usage of nav mesh obstacle.